Okay, off we go. So before we get back into the math, a reminder, so I sent an email to y'all on Friday, I guess it was, about attendance. Right, so remember, attendance does count as part of your course grade. It's not a very big part, but even though it's a small part, it actually can make a surprisingly significant difference. So anyway, it's something you have to take seriously. Again, there's too many of y'all for me to be able to check names by hand. It's just not gonna happen with 90 students in the class. So we're doing it with attendance codes, right? So the point is, you go to the Canvas site. Again, I find that the phone app is awesome, right? Super convenient. In the Canvas site, there is a quiz with today's date as its title. The quiz has one question. The question has that as its answer written on the board, right? And so just type it in, hit submit or whatever it asks you to do, and then make sure, now this is important, and this is a student responsibility, you have to make sure that you actually get that credit. Make sure you have actually hit the submit button. Make sure that you get a little notification that says, I think it'll say like 1 out of 1 points or something like that, right? So make sure that it is submitted and you get your point. Easy process, but again, important. And this is the only way that you can get credit for attendance, right? I can't take a subsequent email or something like that. Do make sure, you have to make sure this is part of your routine. As soon as you walk in the door, you sit down, you do the attendance quiz, right? So make sure that you have that in your routine. Set reminders for yourself if necessary, whatever. But again, student responsibility. The other thing is, do keep in mind, and this is discussed on the website, the class website, that not only is attendance required, but being on time is actually a requirement if you look in the documentation on the website. So the only way that I have to enforce that is by making the quiz actually disappear, right? And so now I understand that if you walk in 3 seconds before the scheduled class time, obviously you can't pull out your phone and do it in 3 seconds. So to give you all, I think plenty of time. Typically, it will be available for 2 minutes after the start of class. Right? Now that should be comfortable time. Once you come in, just pull out your phone. Again, the Canvas app is super efficient, super quick, and type in the number. I think 2 minutes should be comfortable. But that said, don't run it close, right? Don't take any chances. Make sure you're on time. Okay. Has everybody done the quiz for today? By the way, everybody's got that in. Okay. All right. Good deal. One other thing. So you may notice, you may not, doesn't matter. But anyway, today only, I made it a 10-minute after the start of class time, just in case we had some unknown logistical issues or something, right? So that was a first time, one time only kind of a deal. Going forward, 2 minutes after the start of class, so you got to get it done. Okay. Back to where we were. So we were talking about linear approximations, and remember the big idea of linear approximations is that where this formula comes from is it's the unique degree 1 polynomial that satisfies these two requirements. So it's the unique function that agrees with f in value and derivative at the point A. Okay. All right, and so we generalize that to a multivariable function, right? So multiple input variables. And the adaptation, and you can write down a formula, but then you realize that there's really a better way to write it down. And the punchline is, what had been done by the derivative is now done by dot product with this thing called the gradient, computed by that formula. Right? So this thing here called the gradient is playing the role that the derivative played up here. Right? So in a way, and this is a pretty good case, I think, in a way the gradient is kind of a derivative because it's playing the role of the derivative in a sense. And we're going to elaborate on that later. Okay, so that's about where we left off. We did this example, and then we made it to the next page, and we talked about this. I'm going to preempt the notational convenience here because it's really ugly to write it down without the notational convenience. Punchline being when you have a vector-valued multivariable function. In other words, not just several inputs, but also several outputs. Right? And by the way, you can see that up here. Several inputs, like the last example, but now also several outputs, too. Right? In that case, look at this. It's morally the same kind of a structure of a formula. It looks just like the single variable formula, except now the role of the derivative is being played by this matrix. And we talked about this matrix last time. It's the matrix that is assembled out of partial derivatives. That is, to be clear, partial derivatives of all of the output variables with respect to all of the input variables. That gives you an array, right? It gives you a matrix of partial derivatives. That's the thing that goes here. And so again, a kind of a case can be made, right? That this is playing the role of a derivative. Maybe it's kind of a derivative, in a sense. It's a little bit weird to think about a matrix being a derivative, but here we are. Right? So, now I think I mentioned this last time. I'll say it again. Keep in mind that columns correspond to input variables. You'll notice this first column, you're taking partials with respect to the first input variable for all of them. Likewise for the rest of the columns. And then notice that rows correspond to output variables. Notice all of the partials in this row are partials of the first output variable. Right? So you just got to remember that. It's easy to get it switched inadvertently, but just make sure to remember columns correspond to inputs, rows correspond to outputs, and then you assemble your matrix accordingly. If you get that backwards, you will in fact end up transposing your matrix. And that's not the same matrix, and it won't do what it's supposed to do, and it's just crash and burn. So very important to get that straight. Okay. Everybody doing all right? Now I'm going to leave it as an exercise for y'all to confirm that this formula, with this matrix defined as above, satisfies these two requirements. Namely, that this formula, this thing called L, this what we call linear approximation function, mimics f in value and mimics f in, let's be careful about how I say this, all of the partial derivatives. And notice when I say all of the partial derivatives, that is specifically the partial derivatives of all of the output variables. By the way, with respect to all of the input variables. So that's a lot of partial derivatives. Okay, so you don't necessarily have to do this in general. Like if you want to do this for 3 inputs and 2 outputs, something like that, just to kind of keep things under control, right? That's fine. That's no problem. But please do, let's say for 3 inputs and 2 outputs, make sure that you understand how this formula assembles and confirm by direct calculation that these 2 properties are satisfied. Okay. All righty. Moving along. Example. Now this is just a plug and chug, so let's be quick about it. Here's our general formula for linear approximation into which we're plugging and chugging. F is there. The point that we're plugging in is there. You plug this into that, and that value ends up being this. Now okay, let's take a pause. What's up with the value of a function being a vector? Well, yeah, it's a vector-valued function. This function has 3 output coordinates. When you put inputs in, you get 3 coordinates out. Namely, you get a 3-dimensional vector out. So this is actually as expected. This is what you should get. Okay. Likewise for the derivative matrix. Now, of course, in order to compute a derivative matrix, you first have to take the appropriate various derivatives, which, of course, is just a bunch of partial derivatives, which, of course, you all know how to do. Right? So make sure you're proficient, make sure you're glass smooth, reliable, and quick with computing those partial derivatives, with assembling them the correct way. Again, no transposes. Right? And then, of course, you got to plug in to get the actual evaluated derivative matrix. Right? And again, we're just plugging and chugging, and then x minus a, or r minus a is what you multiply by, just like previously. Okay. Whoopsie. All right. Okay. A couple of quick observations. We've already noted that the columns correspond to input variables. We've already noted that every element of a given column is a partial with respect to the same input variable. What I've written here is a slightly different statement. This doesn't just say that the elements of a column are the partials with respect to that input variable. This is saying the entire column is the partial derivative of the entire vector-valued function all at once. So it's a slightly different statement. Ultimately, the point here is that when you take partial derivatives, you do so one coordinate at a time. It's not a particularly surprising statement. It's a true statement. I don't want to get into the weeds of the micro details of why it works. It's just a matter of kind of writing things out in coordinates and everything just works. So not a deep statement there. This next one is a little bit more of an eyebrow raiser. The rows of the derivative matrix are the gradients of the coordinate functions. Right? So I claim, for example, the first row of df is the gradient of f1. Now let's think about why that would be true. Remember, a gradient is just the partials with respect to all of the different input variables. And notice, sure enough, that is straight up the partials with respect to all of the input variables of f1. So it is the gradient of f1. So big. Now, a little fine point, little fine detail. You may notice that in the formula for the gradient, I have commas. Right? Don't forget, comma means new line. Right? So this is actually a column. Right? I write it horizontally for sort of typesetting reasons, because otherwise it takes up too much vertical space on the page, and it's annoying. So very commonly written with commas, but that is a vertical column, you might say, vector. Okay. Whereas this that I'm claiming it's equal to is a row of a matrix. So yeah, they're a little different in that sense, but when I say they're the same, what I mean is the elements of that row and the elements of this, the coordinates of this column vector, exactly the same elements. So that's all. Okay. All right, and then a fussy little distinction. You may recall I made a very brief comment about linear approximations actually not being linear, and this is a little bit silly, but you can look right at this formula right here, this linear approximation formula, and it's not hard to check that this is not linear. The graph is a line. That's not what linear means. Right? Think back to Math219 or whichever linear algebra course you took. Linear is this statement about linear combinations going in, linear combinations coming out. And one of the features of a linear transformation is when you put 0 in, you get 0 out. Not so here. It's not linear. So, okay, fine. Why do we call it linear then? Well, we call it linear because the graph is a line. Right, so it's kind of a semantical thing. We do have a word for this, though, and the word is affine. Not important, but just kind of a neat little cultural point. So shouldn't this have been corrected long ago? Case could be made, but here's the thing. the formula for the linear approximation, the heavy lifting, is done by that matrix. That's what kind of makes it work, right? That's the clever part of the construction. And of course, a matrix is a linear transformation. So it arguably shouldn't be called a linear approximation. It should arguably be called approximation based on a linear matrix or something like that, right? But it's too much of a mouthful, and this is all fussiness. Okay, let's talk about tangent planes. Another flashback to Calc 1. Y'all have seen tangent planes. Tangent lines, I'm sure. Right, here's the problem. In Calc 1 classes, very regularly, they conflate tangent lines and linear approximations. And this is a problem, because linear approximations are functions. Tangent lines are not functions. Tangent lines are pictures. Right? It's a set in the plane, right? It's a shape. It's not the same as a function. Right? Now, they blur that distinction in a Calc 1 class, because in a Calc 1 class, every picture they draw is a graph, pretty much, rare exception. So let's say pretty much every picture is a graph. And when you have this convenient, always the same relationship between functions and pictures, namely you're always using the graph construction, well, you can afford to be sloppy about that because there's no ambiguity. Well, those days are gone. Right? We now have several importantly different constructions for understanding functions with pictures. And graph is simply not going to be used universally. So we have to make this distinction. So please, please, please be careful to note the distinction. This right here is a function. That function is called the linear approximation. That is not a picture in any sense. That is a purely algebraic object. Right? Now, the tangent line is what you get when you say, I want to look at the graph of that function. And when you say you want to look at the graph of that function, tangent line. When you say you want to look at the graph of that function, that gives you that, which is an equation involving two variables. And there is a canonical, if you have an equation and you want to draw a picture of an equation, you draw the set of solutions to the equation, and that's just how that works. And that is the tangent line. If you want to get fussier than I'm being, you could say, well, it's the equation of the tangent line, but it's fine. So anyway, please don't conflate these. Do keep in mind that we're making a choice to look at a graph. Not only do you not have to always look at graphs, sometimes you won't want to look at graphs. Sometimes you will need to look at something else. So this is an arbitrary choice that you cannot assume. All right. So the big idea then is, okay, let's do the same thing. Actually, I can fit these both on. Let's do the same thing to a function with two input variables. Same basic idea. And, well, here's what the linear approximation formula is, right? There's a function. And we can talk about the graph of that function by setting its output values equal to, let's say, z, not that it matters. And then the result is this equation, which describes the tangent plane in the same sense that this equation describes the tangent line. Okay, so anyway, heads up on that. Moving along. Now, the next couple of pages we are going to kind of skip. It makes me a little sad. The inner mathematician in me finds this stuff right here to be some of the coolest material in the course. But this it's too abstract, really, for Math219. This is very appropriate for, let's say, 222. But spending a bunch of time on exactly what precisely and rigorously do we mean by differentiability is actually a big, deep, subtle conversation. And That's cool stuff, and I'm sad we don't have the time to do it. But anyway, this next 2 pages of notes is just kind of addressing this concern of, hey, really though? I mean, can you just write down a formula and just assume that that's actually going to work as expected? That is going to be the linear approximation. Is that going to behave like the way that we think it should? And it turns out that sometimes it doesn't. And it has to do with being careful about not making inappropriate assumptions. And y'all will recall from Calc 1, sometimes functions aren't differentiable. You can't even take a derivative. Right? It's even worse in this situation. When you're talking about multivariable functions, sometimes the function's partial derivatives exist and are fine, and not a thing wrong with the partial derivatives. But the function's still not differentiable. And it's weird. And there's no one-dimensional analog of this. And so, anyway, you can play around with this if you're curious. You don't have to. This is not going to be tested. The punchline is that there's a definition of differentiability. Namely, there's a definition of what does it mean for the formula that we think is the linear approximation actually to work, actually to be reasonably interpreted as a linear approximation. And the condition is that you need this expression to always approach 0 as x approaches a. Oh, that was a typo. Sorry. This is as r. I need to fix that in the next version of the notes. As r approaches a. So where does that come from? Why does that work? Again, long conversation we don't have time for. Okay, so what y'all do need to know is a couple of terms related to this. And so in particular, you'll notice that if I were to kind of put some parentheses, like here and here, you will notice that this part says how much does the function actually change between the starting point A and your new point R. And if you go from A to R, how much does the function actually change? That's called the increment. Terminology is going to be useful. We'll be using it in the future, so heads up. And then on the other hand, that's being compared to this expression, and this is our linear estimate of how much the function is changing. And this is called the differential. And y'all may recognize the notation DF. Okay, so by the way, fundamentally, that's what a differential is. A differential is a linear estimate of the change in the output value of the function based on derivatives. Okay, so heads up on that distinction and on these terms. But and notice this stuff here is not in the box of optional, right? This is part of the course, and you do have to know that. Okay, all right. So here's the problem. Differentiability is important. We need to know when we can apply theorems that require. Oh, I'm sorry. Question. Yeah, go ahead.
Sorry, for the previous equation, how do we use it to actually know whether the derivative exists?
Oh yeah, it's a pain. Yeah, and I'm about to show you a way around it. A nice little workaround. Yeah, and so there are situations where you do absolutely have to use this, but they're actually pretty rare. In great majority of situations, at least in a practical sense, what I'm about to show you, much better. Okay, so here's where we are. Differentiability is important. There's a bunch of theorems, the condition of which is the function has to be differentiable. So I need to know how to decide if a function is differentiable. And I don't want to have to deal with this annoying, big, clunky, scary-looking definition every single time, OMG. So what do? And the answer is we use this very closely related idea called continuous differentiability. And weirdly, very surprisingly, continuous differentiability is easier to define, easier to check, and stronger than differentiability. Right? Stronger in the sense that any function that's continuously differentiable is also differentiable. Right? So it's totally awesome. Right? This is a massively convenient workaround. This is why we can get away with not really dealing with that definition. Because all you got to do, apparently, is check continuous differentiability. You just have to look at the partial derivatives, confirm they exist, make sure that you're not dividing by zero anywhere, right? Make sure that you're not taking the square root or a log of a negative number, right? I mean, just make sure the formula actually can be evaluated at the point you're interested in. And then just check if the function is continuous. And now I'm going to call y'all back to Calc 1. I imagine it probably was. In practice, most of the time, in single variable, looking at single variable functions, the way you know a function's continuous is because a ton of theorems have already been proved that you just get to cite all polynomials are continuous. Boom, right? That's how you know polynomials are continuous. You cite that theorem. Likewise, polynomials, exponentials. Now, you got an asterisk, logs, exponentials, trig functions are continuous, drama, where they're defined. Right? Now, they're not obviously not continuous everywhere. Like tan has a big discontinuity in it, right? But where it's defined, tangent is continuous. Likewise, logs, exponentials, sums, products, quotients of all of these functions, almost anything you can write down is continuous where it's defined. So, now, yes, there are counterexamples amongst, weird situations, but anything that you can write down by way of standard, normal kinds of functions is continuous where it's defined. So this tends not to be a problem. Okay, so let me show you how this works in practice. Here is a hypothetical exam question, right? How do we know that this function here is differentiable? And so here's the argument I'm going to show you. We're going to use this theorem, right? So step one, I'm going to establish that it's continuously differentiable, and then I'm going to cite the theorem and conclude that therefore it's differentiable as desired. Right? That's the kind of the big picture, broad brushstroke. So okay, well, I got to look at the partials. I mean, it's pretty obvious, I think, that the partials are all going to be polynomials, right? You don't even need to really even write them down. They're sort of obviously all polynomials. By the way, we have old theorems that tell us polynomials are all continuous. This right here, then, that the partials are continuous, that is the definition of continuous differentiability. And then I cite the theorem. Therefore, the function's differentiable. Right? So continuous differentiability gives us differentiability. How are we doing? Everybody all right? Please do notice that you do have to actually, and I've written this down in the class website, and I talk about it a lot, and I think it's a really important point that, what is this class about? This class is not about answers. This class is about reasoning, right? Ideas in reasoning. So, it is not the case that you can just kind of write down whatever you want, and as long as these are the last two words of what you wrote, that you have a valid proof. That's not how it works, right? So your reasoning has to actually hold water, right? Your reasoning has to make sense. So notice, you need to cite the continuity. Continuity is one of the requirements of continuous differentiability. So make sure to say that the partials are continuous, because that's the point, right? And I do see a lot of times, very regularly, I see students write the partials are polynomials, and so f is continuously differentiable and therefore differentiable, and they just kind of don't, this doesn't get mentioned. Right? Well, that's a problem. the definition of continuous differentiability doesn't say anything about polynomials. That's not the point, right? The point is that to make this leap, the point is that the partials are continuous. That's what allows you continuous differentiability. Does everybody see that? Right. Another sort of equivalent sort of bad documentation is students will say partials are polynomials, all of which are continuous, and therefore the function's differentiable. And it's again like, oh gosh, but there's a really big point there as to why that continuous partials gives you differentiability. The big point is because that's what continuous differentiability is. Right? Continuous differentiability is a very important sort of step that, if you don't write it down, you're just kind of glossing over a big point. So anyway, please do be careful about this kind of thing. You do have to explain your reasoning, and that means you got to hit the significant points of your argument. Yes?
You said explicitly that they're continuous, which implies differentiability, but you
I hear you. Not quite. The problem there is pronouns. They are continuous, but they is the partials, not the. Does that make sense? Yeah. So you got to distinguish between which of the two functions are you talking about, right? And by the way, also differentiability implies continuity, but continuity does not imply differentiability. So yeah, that's another. It's a one-directional theorem. So you got to be careful with that too. Is that satisfying? Okay. Okay. All right. Another little quickie. Oh, and exactly the point that I just. So I guess I preempted the point. Differentiability implies continuity, but it does not go the other way around. Continuity does not imply differentiability. Absolute value of x is a pretty easy counterexample there. But this fact, we can invoke what's called the contrapositive. Now, y'all probably had a course at some point where they talked about certain logical constructions of, if you have an implication, then you can talk about the inverse and the converse and the contrapositive. Y'all remember all of those kind of terms? Contrapositive is kind of my favorite of those. It's a way to turn one statement into a different statement that's also true. Right? So the fact that differentiability gives you continuity, the contrapositive basically says, well, then if that is not true, then the hypothesis could not have been true. This is called the contrapositive. Right? If the output is false, then the input must have been false. And that's all this says. Right? This is the contrapositive of the blue implication. This is a nice little result here. This is a test. It's not really a test of differentiability. It's a test of non-differentiability. If you have a function that is not continuous, boom, definitely not differentiable. Okay, so useful sometimes. There's an example that follows. It's pretty readable. Give that a glance if you're curious. I'm just going to move along. It's not much to that one. Okay, so let's talk about language a little bit. I've used this term derivative. We've talked about partial derivatives. We've talked about the gradient vector, which I said is a kind of a derivative. And we talked about this matrix df that I said it kind of sort of plays a role. But it's in the spot where we would have expected a derivative to be. So I want to solidify that a little bit. Remember the whole point, one of the points of a linear approximation is that L agrees with F in value and derivative, but more to the point, in value. Right? So F of A and L of A are the same. And then I can take this term, subtract it over to the other side of the equation, no big. Right? And now look at what we've got here. What we've got here is a statement about how if I change the input into F, and if I want to let's just look and see what this says. This says the difference in the linear approximations of the output values. So this is this is on the left our approximation of the output change, aka it's our output differential. Right? Remember, that's what a differential is. It's linear approximation of an output change. So, in fact, then, this thing, df, that I've been calling the derivative matrix, it's the thing that turns input changes into output changes. That is, in fact, our defining characteristic of a derivative. So, df turns input changes into output changes. Linear estimates, of course. So I think this is pretty hard to argue with as a justification. This satisfies our most fundamental notion of what a derivative should be. It is a derivative of some sort. And in fact, if you think about it, since this applies in the general case, right? So this applies no matter how many input variables you have, no matter how many output variables you have. This is our most general form of a derivative. And it is a weird sort of new reality to kind of deal with, right? To kind of get used to. But the word the derivative in a multivariable setting refers to a matrix. So you got to kind of get over this idea for, Calc 1, that derivative is a slope, and of course that means it's a scalar, obvious. Of course, right? Every derivative you ever wrote down in a Calc 1 class is a scalar. It's a number. It's a single value. Not anymore. Now we're looking at multivariable, vector-valued functions, and now derivatives in general are matrices. Everybody see what I'm talking about? By the way, this is kind of arguably, it depends on how you look at it, this is one of our first glimpses into why the math department teaches linear algebra first and then multivariable calculus second. Right? And it used to be different, and there were reasons for that, but it really makes loads of sense to do linear algebra first, because when you get right down to it, what a derivative really is, fundamentally is an object of linear algebra. Linear algebra is the proper language with which to discuss multivariable derivatives. So it makes sense to have a linear algebra course under your belt. Okay. All right. Moving along. Heads up. Sometimes called the derivative, sometimes called the derivative matrix. Okay, fine, whatever. Sometimes called the derivative transformation. Don't forget matrices are always linear transformations. So derivative transformation, common term. Also sometimes called the Jacobian matrix, and thus this alternative notation, JF instead of DF. Heads up on that. Okay. All right, let's see. Okay, so just a picture now. So again, the big idea of a derivative is it's what turns input changes, input differentials. I was at one place in the domain. I'm moving to a nearby different point in the domain. dr represents the change in that input. And from that, if we want to estimate the change in the output, now again, keep in mind that's an estimate, right? Linear estimate. The actual increment, the actual change could be a little different. Right? But we're just doing approximations here. But that thing that turns input changes into output changes is df. That's what a derivative does. Is that cool? By the way, now we can tweak this a little bit in a lovely way. And that is, let's take that same exact story, but let's just divide by dt. And now let's look at what the derivative does. This thing, what does it do? Well, what is dr dt? Let's see here now. That's the derivative of position. I don't know if you all remember from various different contexts you may have seen this, but the derivative of position is called velocity. And so I can reinterpret that the input change as a rate of change. Likewise, looking at the output, right, we get df dt. Well, that's the velocity of the output value of f. And so a different take on what derivatives do, instead of thinking of them as turning input changes into output changes, linear approximation, blah, blah, blah. Instead, you can think of it as something that turns input velocities into output velocities, no asterisk. No, but the linear approximation, so it might be a little off, and we don't know how to quantify that. Right? I mean, the little asterisk is kind of unseemly, really. And this avoids the asterisk, right? As long as the function's differentiable, input velocity to output velocity. Simple as that. So for whatever it's worth, this is my favorite way to think about what derivatives do. I like to think in terms of velocities because, again, it's all instantaneous velocities. It is not an approximation. It is exact. And I just find that appealing. So input velocities to output velocities for your consideration. Okay, the last little observation to make here is really just a kind of a notational thing. Complaint could be made that this argument here started with the vector valued case where df is a matrix and you do a matrix vector product there. But recall, going back a ways, that for the real valued case, the way we had written it down was not with a matrix, but with dot product with the gradient vector. So, I mean, what happens if you take this formula and kind of move things around like we did a second ago? Wouldn't that give you an interpretation of the gradient vector? And yeah, sure, it totally does. Right. The thing to keep in mind is, as we've already noted, let me get back to where we were. So you can do that, and yes, it is true. Dot product with the gradient vector turns input differentials into output differentials. Totally. Absolutely. Gradients are derivatives in this sense. Absolutely. The thing is, it's not really different, right? So I already made this observation that the derivative matrix of a real valued function kind of is pretty much the same thing as gradient anyway, right? This is, let's see here. This is the row vector consisting of all the partials of the function. The gradient is the column vector consisting of all the partial derivatives of the function, right? They're all the same elements. And so matrix multiplication by df, dot product with the gradient, are exactly the same calculation. You start multiplying stuff out, it's all the same stuff. It's really just an alternative notation for the exact same calculation. So don't sweat the distinction. This is a sort of a notational alternative, but specifically when you have a real valued function, so real valued outputs, and this is peculiar to real valued outputs, the derivative, right, dot product with the gradient, yes indeed, is what turns input changes or velocities, take your pick. It's what turns input changes into output changes. Just like the derivative matrix, it's just a different notation. Hope that's cool. All right. Okay, the next couple of pages are pretty readable. I'm going to hit a couple of highlights. There is a subtlety here at the beginning of 2.4, but this is pretty readable, I think. The rest of it anyway. So let's talk about linearity. So the derivative is linear. It sounds like a boring statement. Didn't we establish that long ago? That's the derivative. right? And it turns input changes into output changes, and it's a matrix, and matrices are linear. Where's the subtlety, right? Okay, well, the subtlety is not only is DF linear, D is linear. D is not the derivative. D is the act of differentiation. D is the process of differentiating a function, not the result of differentiating a function, but the process of differentiating a function. D doesn't turn an input vector into an output vector. It turns an input function into an output matrix, namely a linear transformation. So now there's another situation where it's really nice to have already had a course in linear algebra. You all know about vector spaces, right? And you know there's R1, R2, R3, but there's also abstract weirdo vector spaces like the vector space of all functions, or the vector space of solutions to a homogeneous differential equation, or the vector space of matrices of a certain dimension, or whatever, right? Various different kinds of vector spaces. D is linear between these two abstract vector spaces. The vector space of differentiable functions to the vector space of n by n matrices. And saying that D is linear is a very different statement from saying that blue output DF is linear. DF is linear in the boring sense. Vector in, vector out, like that. D is linear as well. So now again, what does it mean to be linear? Well, it means linear combination in, linear combination out, and keep in mind, it is functions that we take linear combinations of, right? Linear combination by coefficients A and B, and we get the same linear combination of the output matrices. So that's what we mean by saying differentiation is linear. Subtle, right? It's you've got to be careful about the players when you think about what this is saying. So take the time you need, let this kind of soak in, think about it. By the way, let me remind y'all, come to office hours, right? Anytime. If you're like, yeah, I didn't really, that was weird, I didn't get what you were talking about there, come on in, we'll talk about it, right? Happy to help. But this is a good point to digest. This example, I think, is very readable. I'm going to let y'all read this example. It's just a bunch of details, the punchline of which is D is linear. And again, details for y'all. And then there's a reference here also to, there's kind of a couple of different cases of a product rule and a quotient rule. And this is all covered in the book. And this is just a matter of writing things down. And it's in the book, and y'all can read. So make sure that you are aware of those rules. And you can even confirm that they're true. It's just a matter of cranking them down into coordinates and cranking it out. Okay. All right, next page. We'll talk, and again, this is mostly readable, right? And I'm just going to kind of hit some highlights, but y'all will recall from single variable calculus that if you have a function, sufficiently nice function, you can talk about the derivative of that function. And then you can talk about the derivative of that derivative. And it's called a second derivative. You can talk about a third derivative, etc., right? You can keep taking derivatives of derivatives. Well, the same is true of partials. So, for example, I can talk about taking the x partial of that function f. The function f was a function of x and y. Check it out, its partial is also a function of x and y. So I can talk about its x partial, or I can talk about its y partial. Just like the original function, I could talk about its y partial. Right? So you get this kind of tree of different possible higher order partial derivatives, And, what's it good for? We'll talk about that in a second. But it's just, something that we're allowed to do because, you can. I mean, why not? So I do want to talk about the notation a little bit. This is an unfortunate little bit of ugliness in notation. Let me zoom on that. So notice what I have here is some function. And notice what I've written down here is the very first thing I want to do to that function is to take its x partial. And then having taken that x partial, the very next thing to do is to take the y partial of that x partial. Now I've written that down in two different ways. Recall, we've got this Leibniz-like notation on top where you say, partial, that you can read. And then we've got this, I like to call it sort of Newton-like notation here, where we just make it a subscript. It's kind of analogous to prime, right? It's just very compact. But you do have to indicate what variable, so we make it a subscript. Well, the thing is, the partial symbol notation is on the left of the function. The subscript notation is on the right. And that just unavoidably puts you into this situation where everything kind of seems backwards. So you'll notice here, I keep the y on the left and the x on the right because, well, of course, you'd lose your mind if that wasn't a standard, right? And then also here I've got to keep these in that order. And so the tragic punchline is that, let me do it like this. These are in opposite orders. And it's really unfortunate, right? But again, we're painted into this corner by I'm going to say inadvertently unfortunate choices that we made early on. So heads up, it's kind of silly, but it's something that you have to be aware of. Okay, let's see here. If I can get this to, there we go. Okay. Now, here's a neat observation. Notice here we took the y partial of the x partial. Here we took the x partial of the y partial. It is not immediately obvious that when you take two different partials but do them in opposite orders that you will necessarily get the same thing back. Right? It's not obvious. In this case, we seem to have gotten the same thing back. How about that? So that's kind of eyebrow raiser. So is this a lucky coincidence or is this a glimpse into a more general fact? And good news, it's the latter. In a broad category of cases that I'll detail in a moment, you can rearrange the order that you take the partials, and you'll always get the same answer either way. So take the partials in whatever order you like, so it kind of doesn't matter. Now, the condition that is required to draw this conclusion is another important thing. The condition is the function has to be what we call CK. So this is just a notation. It's just a notation in terminology. It's just C stands for continuous. The function's got to be continuous. But the K tells you how many partial derivatives, to what degree of partial derivatives also have to be continuous. So, for example, a function that's C2 means the function's got to be continuous, all of the partials have to be continuous, and all of the second partials all have to be continuous. That's what C2 means. Right? You can generalize that as CK. So that's the condition. Now you may say, well, golly, if I have to compute all of those partials just to conclude that changing the order doesn't make any difference, couldn't I just notice that from having just computed all of those partials? Right? And there's a point of view there. But notice that sometimes it's actually really clear. Sometimes it's a freebie that your function is, let's say, C2 or something. So, for example, polynomials. Polynomials, right? I mean, however many partials you want to take of a polynomial, always a polynomial, and therefore always continuous. And so at a snap, without actually computing anything, I know that every polynomial is ck for whatever value of k you like. Right? This is what we call C infinity. So again, sometimes this condition is easier to check, even if you don't compute the partials. And therefore, you get this really nice conclusion that, hey, I can conclude that it doesn't matter what order I take the partials before I've actually computed any of them. Okay. Let me pause on that for a quick moment. How we doing? Everybody all right? Okay. Feel free. That was weird. I just splashed myself. Okay. Moving along. Okay, let's talk about pictures. Y'all remember second derivatives in Calc 1? And there's a geometric interpretation of second derivatives, right? It's about concavity. And y'all probably remember the arguments that got made to justify why the second derivative speaks to the concavity of the graph. Sure. Cool. So what about in multivariable? If I have a function of two variables, notice here I'm looking at a graph. I have two input variables. I have one output variable. The graph, of course, is some surface, and I deliberately drew this to look like a Pringle, right? Like a saddle, just to make it weird. By the way, really hard to draw. It's really hard to draw. I'm pretty impressed with myself for having been able to do that, right? That's one of my prouder achievements in this course. So let's think about what would you expect second derivative to mean. So let's think about, for example, fxx. What does fxx look like on this picture? Okay, well, we have rules here. fxx means I'm taking the partials with respect to x. That means y is constant, and that means I'm looking in the x direction, namely I'm looking in a cross-section for a particular value of y, and then the resulting picture is this cross-section curve. And reminder, keep in mind, I'm interested in taking the x second partial, which means I'm taking this function, this purple, the function whose graph is this purple curve, and I just want to take its second derivative because we're going in the x direction. And second derivatives tell you about the graph, so second derivative tells us about this purple curve, concave down. Right? And so the fact that this cross-section is concave down, let's see, let me make my color choices good here. The fact that this cross-section is concave down is why I would expect fxx to be negative. Or vice versa. If you know fxx is negative, that means that the cross-section in the x direction is concave down. That's pretty expected. Now, notice I am being careful to point out that this is only for the x second partial. We don't want to just talk about the second derivative. There's several second derivatives to have to worry about, right? So what about the y second derivative? What if I look at fyy? Well, that would mean that x is constant. That would mean that I'm looking in this sort of a cross-section, the cross-section curve of which is this. Fyy then is the second derivative of the function whose graph is that purple curve, and this purple curve is concave up, which suggests FYY is positive. Right, so that's the weird thing, and there is no single variable analog of this. We've got more directions, right, in the domain. There's more different directions to point, and different weird things can happen in different directions. And so, yeah, it's more complicated. You can't, this Pringle here, I don't think it'd be fair to call it either concave up or concave down as a whole. It's kind of concave up in one direction, concave down in the other direction. So, yeah, again, strange. Okay. All right, now, those are both unmixed. So, x partial of the x partial, y partial of the y partial. Let's now talk about mixed second partials. What if I want to take the x partial of a y partial? What does that look like? Does that speak to concavity? I mean, I don't know, right? We haven't entertained this question, and there again is no single variable analog of this. This is not just like blah blah whatever example you saw back in Calc 1. Nope, nothing of the sort. We're mixing two different kinds of partials. So here's the way I'm going to think about this. Now you'll see I have a picture drawn here, and this is a weird picture. I'll confess that right off. Notice I have not drawn the surface. I haven't drawn the graph. We're trying to draw a conclusion about the graph, but I don't want to draw the graph because, frankly, it's just really artistically hard, and I think it makes the picture more confusing to have the graph in there than to leave it out of there. Right? So use your imagination. We are imagining that there is some graph surface there. And let's just kind of think to ourselves real quick, what do y partials look like? Well, y partials are slopes of tangent lines in the y direction. So in the y direction, right, here's a bunch of, y directions. And you could imagine to whatever surface the graph is, you could imagine tangent lines, and I'm just making one up here, but maybe hypothetically those tangent lines, again, all in the y direction, maybe they look kind of like this, let's say. So you got to use your geometric imagination here. All right, now there's a temptation to say, okay, well, the x partial, isn't that just slope in the x direction? And no, it's not. Very importantly, it's not. Because we're not taking the x partial of f. We're taking the x partial of this other thing called the y partial of f. We don't have the graph of the y partial of f. I can't talk about the x partial in terms of graphs because I'm not looking at the graph of the thing I'm taking the x partial of. So I'm going to have to take a different point of view on how to think about the x partial, and I'll remind you one of our other points of view is that it says, look, as you start moving in the domain in that direction, how fast is the thing changing that you're taking the x partial of? So that's what I do down here, and I say, well, let's imagine as I go in this x direction, and I'm going to have to do a little hand waving here. So as I'm coming out of the board, as I'm coming out of the screen, my slopes start off about like this, and then as I go that way, it does like sort of like this. Everybody see what I'm talking about? All right. Okay. That seems to be negative here because these y partials, right? So here, the y partial looks to be about -2, and then here it looks to be about -1, and then here it looks to be about -0.5, and then whoops, I missed. Sorry. Then here it seems to be about 0, and here it seems to be about +0.5. Right? And look at those y partials. Look at those values. As I move in the x direction, these values appear to be increasing, which means that x partial is positive. Right? So what we have here is a conclusion that when your x partial of your y partial, when that mixed partial is positive, your surface is going to be doing one of these kind of things. And I think a pretty good way to think about this is there's sort of a twisting happening. Just as a geometric appeal, I've never been able to come up with a good physical visual aid for this, but it's like it's sort of twisted. You might say it's twisted sort of clockwise in the back and sort of counterclockwise in the front, sort of creating a twisted surface. So anyway, that's the take. It is, again, there is no single variable version of this. This is not just like Calc 1 in any sense. This is a new peculiarity that happens when you have two variables. And that's what it looks like. So anyway, tough geometric picture, but there you go. Okay, moving along. Oh yeah, right. So let's see. So we just finished 2.4. You would think we would do 2.5 next. You'll notice on the Bray reorganized, reordered content syllabus, I insert 3.1 in between. This is because it turns out that the conclusions of 3.1 are very handy, and arguably I kind of sort of needed them in a way kind of earlier, but this is, I think, the best place to stick it in. So here we go. We'll go ahead and hit that button. So, yeah. Parametric curves. Y'all remember parametric curves? Position as a function of a single parameter, very often thought of as time, which is convenient. So let's go with that. So position as a function of time. Right? But remember, when we're looking at parametric curves, we are not looking at the graph. And again, this is where you have to be diligent and vigilant about. Don't let your these assumptions that get sort of glossed over in high school math classes that every picture you ever see is a graph. Don't continue with that mistaken perspective. Not every picture is a graph, and when you're talking about a parametric curve, it is not a graph of the parameterization. It's just a picture of the outputs. Only the outputs. There is no t-axis, right, when you're looking at a parametric curve. Okay, so we're going to ask a question then. What sense can I make out of the derivative matrix? Now, we have rules for derivative matrices. Remember, there's only one input variable. Input variables correspond to columns, so the derivative matrix has just the one column, right? And there are, of course, several different output variables, and so there are several different variables to take the t derivative of, so we get a sort of a column-shaped derivative matrix. All right. And how can I think about that? And I am going to assert, let me put a question mark here for the moment. I'm going to assert that that is, in fact, the derivative of the vector-valued parameterization itself. And here's why. Because we already have a definition of a derivative. When you want to do a single variable derivative, notice, by the way, those are d's. This is regular old, good old Calc 1 derivative. Like so. Right? And I can write that down, and everything on that right-hand side I can make sense out of. No problem. In particular, notice here we're just taking a difference of two vectors. Cool. We know how to do that. Here I'm dividing by a scalar. Yeah, not a problem. We know how to divide vectors by scalars. All good. Right? And I am going to sort of sweep under the rug that, yes, we also have to talk about the limit, and this is exactly what you would expect it would be, and we're not going to go off into it. There are some formal issues to be worried about that are not Math219 appropriate, so don't worry about that part. But the punchline is that everything that we do in this expression here Everything is done one coordinate at a time. How do you subtract two vectors from each other? One coordinate at a time, right? Coordinate-wise. How do you divide a vector by a scalar? Coordinate-wise, right? One coordinate at a time. And the same is true of limits, by the way. So the nice punchline is, this is in fact true. How do you take the derivative of a vector-valued function? Well, you do it one coordinate at a time. Okay, so nice little fact. And with that, we now have a point of view on how to think about this derivative matrix. It's that thing right there. It's a difference of two position vectors. That's 2 points on the curve, right? There's a starting point on the curve, you might say, and then there's the sort of, h seconds later point on the curve. And that numerator is that difference, and then we divide by this small value h to deal with the fact that that's the formula, right? And now you can imagine what happens as h gets smaller and smaller. As h gets smaller and smaller, these secant lines become a tangent line. Y'all, I'm sure that's familiar. Y'all remember this kind of story from Calc 1. We approach a tangent line, and the vector itself, if you want to know what's its magnitude, the magnitude is the magnitude of that, namely the distance that you've traveled, divided by the amount of time it took you to travel that distance. That's distance per unit time, that's speed. And so really lovely little result here that this vector, and keep in mind what we're talking about is the derivative. It's kind of the derivative matrix, but thought of as the single variable derivative of the parametric curve. It's pointing the direction that the curve is going, and its magnitude is the speed. That's a pre-existing thing. We already have a concept, the vector that points in the direction of motion and whose magnitude is your speed. That's literally the definition of the velocity. It's a really neat little conclusion there. So now let me remind you, we talked about the calculus of graphs. We made this big deal about, hey, whoa, slow down. The calculus of level sets looks totally different. The way you interpret calculus, if the picture you're looking at is level sets, is not the same as how you interpret it if you're looking at a graph. And we talked about the calculus of what I like to call the literal picture. And that's different too. And what we see here is what I would call our first picture of the calculus of parameterization. And again, this is different too, right? Notice, I'm not saying that the derivative is a slope. It's not a slope. It's a vector. Yeah, it's got certain things semantically in common. Yeah, it's tangent, but it's not tangent to the graph because we're not looking at the graph, right? It's tangent to the parametric curve that this parameterizes. So a little bit different, importantly different. And again, make sure not to blur those distinctions. Okay, so let's see here. Just a real quick second. Oh, so acceleration, very similar story. It's the derivative of the derivative. Y'all know how to do a lot of these kinds of problems, I think. If you have the velocity and you want to know the acceleration, well, as we just mentioned, the acceleration is the derivative of the velocity. And you take the derivative one coordinate at a time. Make sure you're good with single variable derivatives, one coordinate at a time, nothing to it. How do you find position? Let's think this through. We know the velocity is the derivative of position. Well, that means that position is the antiderivative of velocity. Now, again, that's a callback, right, to Calc 1. Y'all did this kind of thing. The only difference is that now our velocity is a vector you're taking the antiderivative of a vector-valued function. Again, good news. That's just one coordinate at a time. Just regular old one coordinate at a time. Right? And again, y'all know how to do antiderivatives. And so you come down to this. And we'll pick up here next time. It looks like we're out of time. Yeah. Okay. See y'all later. See you Thursday. Have a good one.